let me march. Okay. Here's how we'll put index notation to use as well. Many of you know what eigen values are, or in French, les valeurs propres. So if you have a matrix F, then the eigenvalues are the roots of the equation. Determinant of F minus lambda times identity matrix is equal to 0. Okay, if it's a 3D matrix, then it's a cubic equation. If it's a 2D matrix, it's a quadratic equation, etc. etc. In index notation, you would write it as determinant of Fij minus lambda delta ij is equal to 0. Okay? And in 3D, I'll just introduce this Cayley-Hamilton theorem, which says for a 3 by 3 matrix F, the characteristic equation can be written as follows: I2 lambda minus I3 equals 0. I1, I2 and I3 are invariants, and these guys are important, and they will have, you will get physical meanings of what these expressions or invariants I1 and I2 and I3 stand for when you do continuum mechanics. Okay? For the time being, I1 is the trace. So in the language of linear algebra, you would say this is the trace, but there is actually a physical meaning for this. Why the heck am I taking the diagonal components and summing them up? There is a geometrical and physical meaning for this, which we will deal with in the solid mechanics class. I2 is a little bit trickier looking, but still Fij, or minus Fii, Fjj. Okay, this too has a physical meaning, and I3 is the determinant of F. Okay, I'll leave it at that for now, because eigenvalue scares people for some reason. So we will skip that. Okay, moving on. Now we start doing very basic vector calculus. Okay, so we start with the gradient operator. Which is this nabla, some people call it, or inverted delta. It's a vector, and you know, for example, that gradient of a scalar, if you don't know, it's okay. I'm telling you what it is now, is d phi by dx1 e1. So gradient of a scalar field gives you a vector, which is written like this: e2 plus d phi of dx3 e3. Okay? Now that you're all experts in index notation, you can immediately say, look, Harsha, we can write this as EI. Or the ith component of the gradient of phi is just d phi by dxi. Okay. I am normally a lazy guy, and so are the people who worked on or developed index notation. Many people did. They said, okay, look, it's too boring to write d by d and etc. Can we shorten it? And yes, you can. This is another notation, d by dxi of anything, let's say f. You can write it as f, and you put a comma, and that comma represents d by dx, and then you put an I, which says it's with respect to xi. Okay? If it's a scalar, there's nothing before the comma, but if you had a vector dai dxj, now this is ai comma j. Okay? So derivative of ai with respect to xj. It's just another short form. So if you go to our gradient of phi, the ith component is equal to phi comma I. Poof. Small and compact. Okay. How does the gradient of a vector field look now? Gradient of a scalar gives us a vector. So something even higher order than vector, which is a tensor. So gradient of vector v, okay, is equal to, I'll give you the answer right now, and we'll think about it for a second. Vi comma j ei ej. Okay? So there are no, this is the full form, or in its component form, the ijth component, you went from a 1D object to a 2D object here, is equal to vi comma j. Okay? The physical meaning of this again will come into play when we do solid mechanics. For the time being, just note that the gradient of a vector field gives you something called a tensor. Okay? Sort of a way to impute it is, okay, gradient is telling me slope, right? How quickly is something climbing up or rolling down. So if I had a scalar field, for example, that scalar field is, I don't know, topography. Then gradient is telling me, okay, if I were to go in the north direction, how quickly is the topography changing? If I were to go in the east, how quickly is the topography changing, etc. Okay? So that's pretty straightforward to impute. But what if you had, instead of topography, a vector field? Okay? This vector field could be, for example, it's not exact, but imagine loosely you're saying, look, the topography is changing with time. Okay, so it's not enough for me to tell you what is the change of slope in the north or in the east direction. You should also tell me, give me one more information, which is at what time do you want me to calculate it? Which is roughly how this guy is coming about. You have to tell me in which directions I have to take the derivatives here, and for which component of v. Okay? Okay. Then we have divergence of V. That is straightforward. This is dV1 dx1 plus dV2 dx2 plus dV3 dx3, okay, which is nothing but Vi, comma, I. Notice the beauty of comma and index notation here. Since there are two i's with this one object, summation still holds, and the summation is in one dv1 dx1, dv2 dx2, dv3 dx3. Okay? What else? Okay. And then obviously curl in English, or rotation in French, rotation. Del cross V, this gives me a vector object, right? So I'm interested in the height component of del cross V. Well, we don't even have to figure this out now. You can, we don't even have to know the definition. We can use the rules of index notation. A cross B, okay? So I need epsilon ij k, the ith component of this gradient, the jth component of this gradient, and the kth component of V. Okay? Gradient is just doing derivative, right? So this is epsilon ij k d by dxj of vk. Or, in our index notation, this is epsilon ijk vk differentiated with respect to xj. So vk comma j. Okay? There is nothing more one can say with these index notations. All I can say is it's just a matter of practice and doing a few exercises, and all this becomes trivial. You can remember this in the top of your head, even if you have a poor memory. Okay. The last thing I want to do a couple of more things. Let's put the vector calculus and index notation together to prove certain things. So, the rotation of gradient of phi is what? Okay. Gradient of phi, we wrote it down somewhere. It is phi comma I. Okay? And then we want to take the cross product. So this is epsilon ijk. I'll play it safe because I is floating about. I will call this phi comma I. It doesn't matter. The kth component of this guy in brackets, so phi, the kth component is comma n, differentiated with respect to j. So we are taking the second derivative. Okay? If it's too confusing, let's write it out. We are taking del cross d phi by dx n, if you like, and this is nothing but epsilon ijk d by dxj of the kth component of this, which is d phi by dxk. Okay? And these are one and the same. Okay. what can we do here? Sorry, I messed up here. Let's say K here. The K comma J, right? So I need to take the kth component, which is phi K comma J. Okay. Can we reduce this any further? I think we can. Here's how we'll do it. Let's rewrite it. I, J, K, phi, comma, J, K. Okay? Now, I'll say phi is continuous, differentiable, etc. So phi, comma, J, K is equal to phi, comma, K, J. Okay? It doesn't matter the order of differentiation. Okay? You can differentiate with respect to xj and then by xk, or xk then by xj. The order of differentiation doesn't matter. Okay, so I'll do the following trick here. Once you become experts, you will quickly realize that if j and k are interchangeable, and there's an epsilon sitting in this expression 0. But for the sake of sanity, here's how I'll do it. J and K are dummy indices, so it doesn't matter what I use, right? So I will write this as epsilon jk, phi comma jk, plus, excuse me, they are dummy indices, so I can swap them. It doesn't change anything. So ikj, phi comma kj. What do we see here? ijk, ikj. We remember that they are opposite in signs. So this is 1/2 of epsilon ijk, phi comma jk, minus epsilon ijk, phi comma jk and kj. It doesn't matter the order in which I differentiate them, so I can swap them again. And this is a big fat 0. Okay? Again, as I said, once you become experts in index notation, if j and k are symmetric, or if phi comma jk is symmetric, then you'll quickly realize that there's an epsilon sitting here, it goes to 0. Okay. Okay, just one last topic to cover, and we are free. So, obviously I said vector calculus, so calculus involves differentiation and integration, though it was not invented in that order. So be it. We will just look at one integration here, because for my solid continuum mechanics class, this is all we need. What do we need? Well, it's called divergence theorem. Sometimes it's called Green-Gauss-Ostrogatsky theorem, etc., etc. Okay, so the theorem, well, theorems you need sometimes a pretty diagram, so I'll draw a nice little potato. Let the surface of the potato be defined by S. Let V be the volume of this potato, let n be the unit normal to the potato. Divergence theorem states that integral over the volume of divergence of a vector field. I don't want you to confuse with v and v there, so let me call it phi. Okay? Obviously, integrated over the volume is equal to integral over the surface of v dot n integrated over the surface. Okay? Now, there are, made a mistake, that is phi. Okay. Now that may look like a math theorem and all that, but there is actually a physical intuition for this. Imagine you have a well of water, and there is maybe multiple sources of water underneath the well, which are pumping water into the well. Okay? So now your job is to figure out how much water is there in the well. For 1 hour, let's say, how much water did the well accumulate? Okay. You have multiple ways of doing it, of course. You can go with your bucket and start collecting entire volume of the water in the well for 1 hour and then compute the volume. But I'll give you one more piece of information. I will say that the well is filled with sources which are sending water at 10 liters per unit volume of the well. Okay? Unit area of the well, sorry. So liters per meter squared of the well. Then this part is basically saying, okay, I know how much water is entering per unit area of the well. I need to compute the entire volume of water. So I'm going to ask how much water is there per unit volume of the well. Because gradient is just division by some length scale, right? This is, if this is liters per unit area, this operation does liters per unit area per meter, let's say. So per length scale. So this is liters per unit volume. So then you say, okay, I know liters per unit volume integrated over the volume of the well. I have my answer in liters. But let's say you were smart, and all of you are here obviously, so, and you knew divergence theorem, you would say, no, I don't need to do that much work. I can actually poke holes in the well, at the boundary of the well. I can ask myself how much water is coming through the hole. So phi dot n is basically saying liters per unit area in the direction of n. Okay, water will always go in the normal direction, right? Water won't be doing this the moment you poke a hole. So phi dot n is just saying, okay, how much water is coming out per unit area in that hole? And all I need to do is poke holes around the well, sum up the amount of water that is coming per unit area, and that gives me the amount of water in the well. Okay, this is a bit of a long-winded explanation, but the basic notion of divergence theorem is if you have a volumetric quantity, like gradient of phi, okay, there is and you want to measure some property of this volumetric quantity, there is an equivalent surficial or areal quantity computed correctly that will give you the same quantity. Okay? Fair enough. That's in fancy vector notation. In index notation, well, we are experts now. What is this telling me? Phi, del dot phi is phi I comma I dv is equal to integral over the surface. Phi dot n is phi I ni ds. Okay? This may not look too useful now, but when you come into more complex quantities, for example, a tensor, okay? And don't worry about the tilde notation for now, etc. This is the tensor itself dotted with a unit normal ts. Okay? Or in index notation, and this is where the power comes. It's a tensor, so it has two components, comma I, because I'm taking the gradient, dv is equal to integral over the surface. And here's how to remember which, okay, so I have aij here, and I obviously need n, but what is it, ni or nj? You may be confused. Don't worry, it's basically whatever component is being differentiated. So this is with respect to I, so this is ni. Okay? And that's the index notation version of divergence theorem or Green-Gauss Usodowski theorem. So I will do a very, very quick verbal summary now. Today we completed index notation and elementary vector calculus. Index notation is a compact form of writing long, complicated expressions, or a lazy man's best tool. Index notation, we learned about the rules of indices, we learned about summation convention, we learned about Kronecker delta, we learned about the permutation tensor, we learned how to take dot products, vector cross products. You were introduced to some funny object called a dyadic product, but that's something we will see in the future. Then we immediately jumped into vector calculus. You got the definition of gradient, divergence, and curl or rotation. You were introduced again to a funny quantity called a tensor, which is the gradient of a vector field. We will see that again later on in the class. And you learned about the divergence theorem. So I'm looking forward to meeting you physically in the class sometime in the coming weeks. Until then, good luck. And feel free to go through the notes and work out the exercises, because the only way to actually really become comfortable with index notation is to actually do a few exercises. These are very trivial. So good luck. Bye.